All right, last thing for today is talking about the rule of 3, also known as the rule of 5. So if we're going to make a vector class, let's say, and you guys are going to make a vector class on Friday, and this class is going to have 10 elements in it, hard-coded. In reality, the vector class will grow, like when you actually make it. We're just going to hard-code it at 10. The class under the hood is going to have an array pointer and a size, which is how many elements are in it. And then we're going to have capacity, which is we're going to hard code it at 10 right now. In the future, the capacity will grow. Okay. So we're gonna make a very basic vector class. It can't grow. Right now, it's always going to be size 10. Okay. So we're going to go through the process of proper class design for making a very super basic vector class. You guys with me? So step 1 is make all the member variables private, which they are. Class is default to private. What is step 2? You guys remember the quiz? What happened in step 2? Constructors, good. Okay. So vector 10, we're going to make a default constructor. And this is going to set array equal to new int 10. This is going to allocate memory off the heap. And it's going to allocate 10 integers, also known as 40 bytes, like that. All right. And size and capacity, we're going to default to 0 and 10, so we don't need them in there. And if you have a constructor that news something, you need a destructor that will delete it. So we need a destructor. Every new needs a delete. So it's called the rule of Sith. Every master, there's an apprentice. Every new needs exactly one delete. Okay. And that's how we free the memory. So what this is going to do is when we make a variable of type vec10 down here, vec10 bob, this is going to secretly call the constructor. And when it goes out of scope, which is here at the close parentheses, this will secretly call the destructor. This model of coding is called R resource acquisition is initialization, array. We say for short RAII, array resource acquisition is initialization. It's kind of a dumb acronym. It doesn't mean anything to people, but basically it means you put your news into your constructor, you put your deletes into your destructor. And then if you, at any other time, mess with those things, you have to make sure, like, to put it back the way it was before, so to speak. Like if the vector grows, when a vector grows, it duplicates all the elements into the new. Let's see, picture this. So when you push back into a vector, if the vector is full, like you might have internally, a vector is usually over allocated. Like you might have room for 10 and you've only got 2 people in it. As you push back, you'll put more and more things into the back of the vector. When it finally runs out of capacity, then what happens is it'll allocate a new array of size double the old one, copy the elements over, and then mess with the pointers and deallocate the old one, and the old one's now pointing at the new one, and then everything's good to go. We'll do that on Friday. And the and so that reallocate is going to have a new and a delete in it to keep everything balanced. So you have to be a little bit tricky if you're doing anything outside of the constructor and destructor to put everything back the way they were before. But basically, the general rule in computer science and C++ at least is every new needs a delete. In Java, you don't have deletes, you just only have news. Okay, so what else do we need in our array class here? We need we need an at. And we're going to return our square bracket, IDX. And we should probably do some bounds checking too. So if we make vector10 bob, what we want to be able to do is say bob.at7 is equal to 42, cout bob.at7 and have that work. Okay, so what do you guys think this is going to print to the screen? This is like our getter and setter, basically. So this is both our getter and our setter here. So what do you think that's going to print? 42, cool. All right, so 47. So we need to add some bounds checking though, right? So this is the index, and the only valid indices are 0 to 9, right? So we have a capacity of 10. I should probably use capacity here instead of hard coding it, right? Yeah. What sort of sanity checking should we do here? What should we put here so that we never go out of bounds? Like it's professional pride to write code that never goes out of bounds, right? So what do we do? If index is less than 0 or index is greater than capacity is close to correct. It's close to correct. Is 10 a valid index? If index is greater than 0, 0 is valid. All right. 0 is valid, 9 is valid. Okay. If the index is less than 0, or if the index is greater than or equal to the capacity, that's the pattern you have to get used to. Then we will throw out of bounds, out of range error. Whatever. Okay. X there. So if the index is less than 0, or if the index is greater than or equal to the capacity, we throw an exception, kill the program. Otherwise, we will return the element. And the cool thing about this is we're returning a reference here. And so by returning a reference, it's actually returning the actual element. So you can actually set it on the left side, right? It's both a getter and a setter. You can get the value like this. You can set the value like this, and that's all because of that little ampersand right there. Okay. So ampersand there. But we're not exactly correct yet. And the reason for that is because we're going to simulate an actual vector, right? And when we start off with a vector, it's size 0, essentially. Capacity is just kind of how big it is under the hood, right? When you have a vector and you're holding 30 elements, under the hood, it probably has 50 elements allocated or something. You don't really know. Size is actually how many people are in the vector. When you call dot size on a vector, it tells you how many people are in the vector, not how big the capacity is. That's a completely different thing. So actually what we want here is if the index is less than 0 or if the index is greater than or equal to size. Okay. So we're going to need another function called pushback. Okay. And pushback here is going to put a value, put x into the end of the vector. Okay. So how do we do this? We've got an array, it's got 10 elements in it. Maybe we got 4 already. And when we call pushback, we want to push this new guy, 9,000, whatever. We want to put it at the end of the array. How do we do it? That's what I just said, Luke. The ampersand there gives you the actual value from the array. It's not a copy. That's what allows you to set it. Okay. Vector.pushback. Yeah, no, you can't call vector.pushback. we are writing pushback. How do we write the pushback function? Right? The get a picture of it. Here we go. So, thank you, ads. So when you have a vector, you've got capacity, because under the hood, like I said, the array has been allocated bigger than what you need. Because when you run out of capacity, you have to make a new array that's twice as big. It's usually twice as big. It doesn't have to be. Usually twice as big. And then all these elements get copied over to the new one, and then the new element gets pushed into the back. So we've got the beginning of the array. We've got size. Here they're using an iterator. We're doing it with an integer. It's going to work out mathematically the same way. And then we've got capacity. Again, they have an iterator. We have an integer. So if this is our current state of the vector that we're working on here, we've got 5 people in the vector currently. So size would be 5. Capacity would be 9, because they have 9 slots in the array, if I'm counting this right. Yeah, 9. And we want to call pushback, and we want to push 9,000 into the vector. We don't have iterator support for this, so don't worry about that. So 9,000 needs to go here, in this spot right here. You guys understand? So make a new array. We don't need to make a new array. We've got room. We're under capacity, right? So we don't need to expand. Well, I mean, yeah, size will need to go up for sure. But as long as we're under the capacity, we're good to go. Like this will work. So vector size equals integer x. I get what you're saying. You want it. So if we have a size of 5, then slot 5 is going to get the new guy, right? Is that what you're saying, Brandis? So if we're got size 5, this is slot 5 here. So vector.at5 equals the value being passed in. Yeah, that is correct. But we need to do some bounds checking. Maybe we'll do that second. So we'll say r square bracket size is equal to x. That's it. And then size needs to be incremented. Yeah. But we need to do some bounce checking here, right? What kind of bounce checking? My chair keeps sinking downwards. I think I need a new gas piston for it. What kind of bounce checking? What kind of errors could occur here? What do you guys think? Vector.size equals integer x. Yeah, except size isn't a function call. It's just like I said, we're just using an integer here. It works just as well. If the size is greater than the capacity is very close. I get what you're saying again, Brandis. Like I get what you're saying, and so let's do that. So we need to check to see if our vector is full, right? If our vector is full, in other words, like on our example here, capacity is 9, and if size 9, if capacity is 9 and size is 9, we're done. There's no room at the end. Sorry, baby Jesus, you got to go to the manger. You know what I mean? So if capacity is 9 and size is 9, we can't insert anything new into this version of our vector. On Friday, you guys will write the code to double the size and copy the elements over and things like that. When size reaches capacity, expand capacity. Yes, that's what you guys are going to do for your next homework assignment. But for now, this is a vector 10. It's always 10. There is no growing. There's no room at the end. We just throw an exception, say, sorry, we're done. Okay, so if size is greater than or equal to capacity, then throw runtime error or something like that. Sorry, vector is full. Something like that. Okay. And there we go. So this code here won't work anymore, right? We can't access element 7 because we've never put anything into the vector using pushback, right? So if we try running this code now, it should throw an exception and die. Good. So what we're going to have to do is say bob.pushback. Let's just toss in a random number from 0 to 10. And then let's just print out the whole vector. Okay. So we're going to push back 10 numbers. We're going to then override the 7th number and change it to 42. And then we're going to print out everybody in Bob. Okay. Maybe I should put some separators in there. Okay. Here's before, and here's after. So you can see that element 7 has been successfully changed to be 42. 0, 1, 2, 3, 4, 5, 6, 7. Okay. So what do you guys think? Looking pretty good. If we try setting this prior to there being an element 7, then it should throw. Yep. Good. So looks like everything's working. Okay. So there is one problem remaining though. Okay. There's one problem remaining. And remember how I said we're talking about the rule of 3? The rule of 3 is that if you have, if you're allocating memory, which we're doing here, anytime you have a new and a delete, the rule of 3 says this. If you are allocating memory or similarly doing stuff with pointers, you need a destructor, you need a copy constructor, and you need a operator equals. Okay. And the copy constructor gets called anytime you copy a variable. Okay. What does that mean? Vector 10 Sydney equals Bob. This is going to call the copy constructor. So it's going to make a copy of Bob. Okay. So what's the problem with this? Anyone know? Seems harmless enough. Crash. Crash. In fact, if I comment out all of this code, and all we have is making Bob and Sydney, who's just a clone of Bob, if that's all we have, it might have been optimized away. Interesting. Crash. Yeah. All right. The optimizer saved our bacon that time. Badly. Yeah. Crash. Crash. Something, something shallow copy, something, something deep copy. Yeah. What's happening here is we didn't write a copy constructor, right? The compiler makes one for you. If you don't write an equals operator or a copy constructor, which is how you do things like this, copying one type to another type, it just makes one for you. Neat. But let's look at what's actually being duplicated. So Bob has a pointer to a chunk of memory, right? Now Sydney does too. And in fact, Sydney and Bob are both pointing at the same chunk of memory. So when Bob goes out of scope, it deletes that chunk of memory. When Sydney goes out of scope, it deletes that chunk of memory, same chunk of memory. And so you get a double free error and it crashes. Even worse, watch this. Even worse than crashing. Even worse than crashing. Let's give Bob basically any change made to Bob is made to Sydney as well, because they're both pointing at the same chunk of memory. So when Bob you know, reads and writes to the chunk of memory, Sydney will read and write to the same chunk of memory as well. So this is actually extremely dangerous because they look like two different vectors, but they're not. They're both actually sharing the same pointer, because that's all the copy constructor does by default, is it just copies all the member variables. And if it's a pointer, then you're in trouble. So it's too much of an exact copy. It's literally two people pointing at the same address. So that's why anytime you're messing with pointers and things like that, you have to have a destructor, you have to have a copy constructor, you have to have an operator equals. And then there's also what's called the rule of 5, which means you also need a move constructor and a move assignment operator. Don't worry about those for now, though. So let me show you how to write a good copy constructor for a class like this. So copy constructor gets called anytime you do something like this. Anytime you set a new guy equal to an old guy, it should copy all the elements over. Or if you call a function, like if you have a function that takes a vec10, not by reference, but by value, this will call the copy constructor as well. Okay. And if you call that foo function, it will make a duplicate of Bob, and the duplicate is going to be pointing at the same thing as Bob. And when foo goes away, it destroys Bob's array, which is not what you want. This kills Bob right here. Bob dies when the duplicate dies here. You understand like how bad this is? Like if you do a call by value, it's supposed to just clone you, and the clone can go away and die, and you're still the same. But here you're cloning Bob automatically, and when the clone dies, it's pointing at the same chunk of memory as you. It kills your memory. So you have to have a copy constructor. You have to have an assignment operator. What is the syntax for that? Glad you asked. Okay. So a copy constructor is a constructor, so it's got no return type, and the name of the function is the same as the class. And it's going to take, by const reference, another vec10. We call it other. So this clones other into us. And so what we need to do is we need to copy all the elements from other into us and make news and things like that. Or let me show you the programmer move. The programmer move, delete. So this tells the compiler, don't make a copy constructor for me. If you ever try copying me, don't allow it. It's a compiler error. This is the pro gaming move. And this is honestly, like when I'm coding professionally, there's a lot of classes that should just never be duplicated. Like if I'm making a scoreboard for a video game and you can read and write to the different teams, you know, the Eagles have 22 points. Okay, give them 5 points. There's no reason for that scoreboard ever to be duplicated. And so I will delete the copy constructor. So if I accidentally pass it like this by value, that won't work. You cannot pass to Bob. That will not work because there's no copy constructor now. I've deleted the copy constructor that the compiler makes for me. And so this prevents me from accidentally cloning my data. And this is actually, I'm saying it's programmer because it's lazy. It's lazy programming instead of having to actually duplicate it correctly. But a lot of the times, like I just don't want to make a copy of my variable type. And so I just delete it like that. Likewise, if I have vector 10 Sydney like that, and I say Sydney equals Bob, this is going to call what's called the operator, the assignment operator, aka operator equals sign. Okay, and so this is calling copy constructor. So anytime you pass a value by value, it calls the copy constructor to make a copy of it. And anytime you initialize a variable with another variable, this calls the copy constructor as well. Okay. But I've deleted the copy constructor, so the line of code will not compile. Keeps me safe. Okay. Now the assignment operator, and the assignment operator is different from the copy constructor, and it usually does exactly the same thing. So when you write a copy constructor, your assignment operator is usually exactly the same code. It's just the assignment operator takes place after the variable's already been made. And so it has to be different because Sydney here is actually going to allocate its own memory. And so that would need to deallocate Sydney's memory and then copy over Bob's memory and stuff like that. But we're just going to delete that one as well. So we're going to say vec, let's say void operator equals sign const vec 10 by reference other equals delete. Done. So now if we try duplicating Bob into Sydney that way, it doesn't work. The compiler normally will generate those things for you, but here we've deleted it. We told the compiler, don't make it for us. Delete it. And so this is how you can protect yourself. This is honestly how I use the rule of 3 in most cases, because most of my things that are involving pointers are usually things I don't actually want to clone. They're actually things I usually don't ever want to make a copy of. That said, for a vector class, does it make sense to copy a vector? Sure, it does. And so if I was making like the standard library vector class, being able to say vector, Steve equals vec, that makes sense. That's going to copy all the elements from vec into Steve. That's fine. But in reality, a lot of the times you will see me just delete these things. You can't copy it ever. And so that's the pro gamer approach here. If you just set the function equals to delete, it will remove the compiler generated functions for us. Okay. Do you guys want to see the way you're actually supposed to do it? Or is this good enough? Programmer, exactly. All right. So the actual way we're supposed to do it is Sydney is supposed to make herself into a clone of Bob. And so let's come over here and undelete it. Actually, I'm going to leave these just commented out so you can kind of see them. Okay. So what you're supposed to do is this. So Sydney is going to make her own size 10 array, and then she's going to say for and I equals 0, I is less than other dot size plus. So for every element in Bob, we are going to copy Bob into us. Array I is equal to other dot array square bracket I. Like that. So we are copying Bob. So like if Bob has 5 guys, 5 times, we're going to copy Bob 0 into R0, Bob 1 into R1, Bob 2 into R2, Bob 3 into R3, Bob 4 into R4, and we're done. And then we need to set our size equal to Bob's size. We're good. That's it. So because we did this, our pointer is different from Bob's pointer. If we don't have this, it just makes Sydney's pointer point to the same thing as Bob's. By doing this, we have our own chunk of 40 bytes of memory. Bob has his chunk of 40 bytes of memory. And then we just look at, okay, Bob, how many do you have? 5? Okay, we're going to copy 5 elements over. And we're done. Just have to make sure we set our size to 5 as well. And then the assignment operator is going to be very similar to this, except we are not going to allocate memory because we have already allocated memory. So we are going to do this. And we're just going to do this. Because we've already done our new. Right. When we make Sydney here, that allocates 10 ints or 40 bytes of memory. So now that code, redeclaration of Sydney, fair enough, So no more seg faults, no more crashing. That's the proper way of doing it. So you can either make, this is using the copy constructor, or we could use the assignment operator like that. So Sydney's going to allocate 10 ints, and then it's going to copy all of Bob's elements over without doing a new. So there you go. So this is like probably 2/3 of your homework this Friday. What you have to do on Friday is make a vector class that when it runs out of capacity will allocate a new array that's twice as big, copy all the old elements into the new elements, delete the old pointer, and then set R to point to the new guy. And some other stuff as well. But that's the basic move that you're going to have to make on Friday. Any other questions about this? The move constructor, move assignment, we'll talk about those later in the semester. But yeah, I would just delete those as well. Like honestly, like like I said, most of the time when I'm working with pointers and things like that, I don't actually ever want to clone it, usually. And so I just delete, I delete the copy constructor, delete the assignment operator, delete the move constructor, delete the move assignment. No, don't ever delete. Don't ever duplicate me. No. and it honestly, it works pretty well. But yeah, there are times where like, yeah, you want to make a copy actually of a vector, and then you have to do what's called a deep copy, which is what this is. So this here is called a deep copy. Without it, we get a shallow copy, which causes crashes. All right, that's our lecture for today. Hope you guys enjoyed it. And so why would you want to make your own vector class? Besides for the homework? You wouldn't. You wouldn't. Maybe you would. But no, normally not. Normally not. The reason why you would want to make your own data structure is if you have either a special need, for something. Like maybe a vector that allocates off the stack instead of off the heap, something like that. Like if you have a small vector, you probably save some time if you're always making vectors of size 3 or 4. It would probably be faster to stack allocate than heap allocate it. Like in gaming, EA has do you guys know EA? It's a gaming company. Like these guys. EA has their own version of the standard library called the EA Standard Template Library, and it's their version of the vectors and other data structures you're going to learn in this class. And they have a high performance version of it, and so they're I don't know if they have timing on here, and so benchmarks here. Benchmarks, it's just benchmark code, not the results, whatever. But anyway, so they've benchmarked their code, and they've found that their version of the standard template library classes is faster than the ones in the standard library. So the Entertainment Activision, yeah, classic one game every year. Yeah. So there are times when you have performance requirements where you want things to be faster, or you have like some sort of special need and you need to write your own data structure. So when I took this class back in the day, there wasn't a standard template library. There wasn't a vector class. There wasn't a set class, det class, list class. So every time you went to work for a new company, you would write all of these data structures by hand yourself. And so you had to be pretty good at it, because if there was any bugs in your data structure, your code's going to just crash. You're going to have a hard time with your application. So nowadays, I would recommend, Burford, to answer your question, I would recommend just using the standard library vector most of the time. But this is a data structures class, and so by writing it, you will understand what's happening when you call pushback on a vector. For example, how long does a pushback take? Remember how we talked about big O last time? Big O is the order of how many operations it should take to do something. If you wanted to print out 1 million elements in a vector, how many operations, and by operations is kind of this nebulous concept, but how many operations would it take to print 1,000,000 elements of a vector? What do you guys think? It would take a million operations. And if your vector was 2,000,000, it would take 2,000,000 operations. And if it was of size 3,000,000, it would take 3,000,000 operations. So that's something called order n, where the running time of the algorithm is print all the values in the vector. The running time of the algorithm is linearly proportional to the size of the vector. So as the vector gets bigger, the amount of time it takes to print everything gets bigger. Order 1, on the other hand, means order 1, constant running time, that purple line at the very bottom there. That line means no matter how big the vector is, it doesn't take any longer to do the operation. So for example, do you guys know how to print the last element of a vector? So if we got back here, 10, 20, 30, 40, 50. If we wanted to print the last element in the vector, how do we do that? Vector.end, would that do it? Nope. Vector.begin plus 4, would that do it? Would this work? Nope, because that's pointing at 50. It's not actually 50. So, I mean, we could dereference this, maybe. This is a pretty garbage tier way of doing it, but it would work. There we go. We got 50 that way. What's a better way of doing this? What's a better way of printing the last element in a vector? Vector.at, vector.size minus 1. Oh, Lord. No. Back. Back exists. That just gives you 50. So that gives you the last element of the vector. Yeah, there's 50. Right. Way easier, you know. And so what's the running time of back? If your vector is size 1,000,000, does it take 1,000,000 operations to print the last element, or does it take 1? And again, 1 is, you know, there could be 3 lines of code or something, but an operation in this, the way I'm using it, is a nebulous concept, but it's 1. Yeah, you're exactly right, Marsh. It does not matter how many elements are in the vector. If you have 10, 100, 1,000, 1,000,000, the running time of back will be constant. It's constant running time. So it could be 3 lines of code, it could be 4, whatever. But it's always, you know, it's always the same amount of time to print the end of the vector. What about if I wanted to print the front of the vector? Did you guys know this existed? You print the front of the vector this way. What about that? Is it, you know, is it order 1 or order n? What do you guys think? Print the first element in the vector. Order 1, okay. Now, what if we wanted to insert something at the beginning of a vector? Like, what if we wanted to put someone before 10? What's the difference between begin and front? Begin gives you a iterator, right? So if we said cout vec.begin, that gives you an iterator. You can't print an iterator. You could dereference it, like we could do this. And this is exactly equal to vector.front. Dereferencing the pointer to the beginning is exactly the same thing. Okay. Yeah, if we wanted to put somebody before 10, yeah, that's going to be order n, right? Because we're going to have to move all the elements 1 to the right and then insert something at the beginning. But if we had a deck, we had a deck, deck actually has a push front. And this one is order 1. So this is why all this stuff is important, because a vector is order n at pushing and popping off the front. Because every time you push or pop off the front, you have to move all the elements at the end, either 1 to the right or 1 to the left, you know, to make room for it. With the deck, you don't. So some people just like, oh, you should just use decks for everything because you're just like vectors, but better. Yeah, but decks are like 30% slower than a vector. So if you don't need to push and pop off the front, use a vector. If you do need to push and pop off of the front, use a deck. That's why we take data structures. Because the whole point of this data structures class is so that you learn what data structures are good at what tasks. So you use the right one for the job. And you don't turn an order 1 task into an order n task, because that blows up your running time. Okay. But the running time of push back on a vector, what's the running time of that? Now that you know what happens when you push back, right? It can reallocate and copy all the elements over. What is the running time of that? Is it order 1 or is it order n for pushback? And this is why, Burford, to answer your question, why do we need to write a vector class? Is because you start understanding what's actually happening here when you call vector.pushback. In CSI40, you can use it, but you might be unpleasantly surprised in the real world where your code runs slow. So a pushback on a vector is order 1 if you don't reallocate, as Olson said, and order n if you do. But here's the kicker. If you look at the documentation, it's going to say it's order 1 amortized. What the hell does that mean? CPP reference vector pushback. The heck is order 1 amortized? Complexity. Amortized constant. Constant's order 1. What the heck is amortized? Mort? Death? What does that mean? What that means is on average. So if you push back 1,000,000 times, it's going to average 1,000,000 operations. So it averages out to 1,000,000. But some of the times it does an order n operation, but it only does those order n operations once every n times. So n divided by n is 1. Okay. So that's why we double the size of the vector every time instead of increasing the size by 1 or something. So that we only, we only have to reallocate more and more rarely. So once every n operations, we do n work, n divided by n is 1. And so that's great. It's order 1, but you might be like timing your code, and every so often you get these like hitches in your code. Like your game's running at 15 frames a second every so often, and you're just like, I don't know why. Like it's running at 120 frames a second, and then we get 15, and then it goes back to 120, and I don't know why I'm occasionally getting these glitches in my code. And it's because if you understand what's happening here, every so often that order 1 turns into an order n, and your code will slow down. If you've got 1 billion people in a vector and you trigger that reallocate, your game's going to hitch for a second as it copies 1 billion numbers over into the new vector and deallocates the old one. You guys understand? So by writing it, then you internalize all of these different trade-offs into your head, and then you never write one yourself again, ever. So in this semester, you guys are going to be, this lecture is proof of vectors. In this class, in this semester, you guys are going to be writing all of these standard library classes. In parts, you internalize them, in part for job interview questions, where they often make you implement these things from scratch. But also just so that you understand the trade-offs, because that's really what we want you coming away from data structures with. Is like, when should I use a vector? When should I use an array? When should I use a hash table? And understanding all the pros and cons and the trade-offs. Like, vectors are great, but every so often they're going to hitch, but well, if you don't want hitching, the person will say vector reserve. And so if you don't want the hitching, you can call reserve, and that will change that hidden, the capacity will up the capacity to 1,000,000. And so you don't have to reallocate it 10, 20, 40, 80, 160, 320. You understand? So if you up the capacity, like if you're going to be using roughly 1,000,000, 1,000,000 integers in here, you can up the capacity, and then that will make your performance go much smoother. That's the point of this class. It's going to take you to the next level of understanding. Okay. Everybody make their own standard libraries like a bunch of wizards. A lot of people do. And to be fair, a lot of the standard library stuff in the standard library is not super performant. Like, there's better ways of doing it. Hash tables in particular. the hash table implementation of the standard library is kind of D tier, maybe. It's not even mid tier at this point. It's okay, but it's not good. Like the state of the art in hash tables is like far super. Like it's just way over here, like the S tier hash tables, and the standard library is like way over here in performance. So, you know, sometimes, you know, like the standard library is like good, but it's not great. And so, you know, after you take this class, you could probably write your own more performant version of a hash table or something like that. All right, that's it for today. Thanks for coming out, guys, and I will see you guys on Wednesday. Peace.